So number 24 shows a section of a long, thin-walled metal tube of radius 3 centimeters and a charge per unit length of lambda of 2 times 10 to the minus 8 coulombs per meter. The question is, what's the magnitude of the electric field at a radial distance of r equals r divided by 2? Now, a quick reminder in this case, this one then is going to ask us, we're trying to find the electric field on the inside. Now, if you're trying to figure out the electric field here, again, we could do a little closed cylinder in here. And if we use Gauss's law, how much charge is enclosed inside of this? Well, the answer is there is absolutely no charge inside of the surface. And so the electric field should be 0 due to the charge on the outside, because none of it's inside of it. So the answer to A is kind of trivial. It's 0. Now for B, it gets a little bit more exciting. We actually have to apply Gauss's law completely. And to do that, we're going to create another cylinder outside this other cylinder, where r here is going to actually be equal to 2r. Now I'm going to leave it as a variable because this last part of this question actually wants us to do a graph. And so I'm going to do this as a sort of general one first. So solving this, we know that the electric field through the outside skin of this thing is going to be uniform because it's all equal distance away from it. So I can move E outside of the integral out here. Plugging in what we do know then, we're also going to have to know, I'm going to say the length of this thing is L, where my cylinder that I'm drawing around the outside is also of length L. So from here to here. And then we can actually do a little bit of work. What's the surface area of my cylindrical shell? Well, the answer is the flux is only going to go through this outside skin of it, not the two endpoints. That surface area is just going to be its circumference, 2 pi r, times the length of my cylindrical shell. How much charge is inside? Well, that's just going to be equal to lambda times the length of my shell. Again, remember, lambda is the charge per unit length. L cancels on both sides, and I have the general expression that looks like this. The electric field around the outside of this is just equal to lambda over 2 pi r epsilon naught, where everything here is a constant except for r. R is how far you're away from the center, so it drops off as a 1 over r curve. Using that equation, then I can now actually plug in some numbers. We know what lambda is. We know we're twice the radius. The radius is 3 centimeters, 0.03. And if you solve that, you'll get the correct answer, or answer if you round to 2 sig figs, of about 6,000 newtons per coulomb. C, graph electric field versus R for the range of 0 to 2R. So in this case, I actually went and graphed a little bit further. Here's electric field. Over here on this axis is distance, x, and we know that the electric field inside of this thing is 0. So for the first part here, just plain old 0. But then what happens on the outside? Well, then it goes to this formula right here. So all of a sudden at the radius, it jumps up. I'm just going to draw a little dotted line here. You don't have to have the dotted line, but just to sort of let you visualize this. What's going to happen? It's going to suddenly jump up and then drop off as a 1 over r curve. And I know I probably didn't draw, I should probably put the 2r over here somewhere. It's going to drop off to about half the value by that point. Hopefully this makes some sense to you. All right, have a good night.